Okay, so this is Game 2005 Assignment 2 for Sarah Gowdy. We're going to start with our package script. We start by declaring our variables for angle, speed, start height, delta time, and velocity. And then we grab a reference to our game physics script. In Update, we are launching our projectile with the space key. We calculate our initial velocity vector using the launch angle and speed. We set the initial position and draw debug lines showing the angle of direction for 2 seconds. Then we call our calculation function to display flight details, but we'll come back to this. In our fixed update, we store the previous position of our object, update the position of the object using its velocity and delta time, and we also draw a debug line in green to show the previous path. We apply gravity to the velocity, adjust the velocity based on mass, and draw another debug line in red. As promised, we come back to our calculate flight details. We calculate the horizontal and vertical components of velocity. We define gravity at 1.6. We calculate the total time the projectile will be airborne, and we calculate the range using horizontal velocity and time airborne. Moving on to game physics. Nice and short, in our game physics script, we declare mass, gravity, and velocity. Calculations. We declare our variables for speed and gravity. Then we create a list of all our angles to perform calculations on. In Start, we loop through each angle in the list, calling our calculate and debug function each time. In our calculate and debug function, we use our angle degrees here. First, we convert degrees to radians. Then we calculate horizontal and vertical velocity. Then we calculate total airborne time and range traveled in meters using those formulas. And then we debug our results to the console. So if we take a look at what that looks like, as soon as we hit play in our console, we're going to see everything in our list, starting at 3.9 degrees, then moving to 6.42 degrees. It will list everything out. It'll list the time airborne and the range in meters that it went. So I don't know how much of this you want to see, so I'll just kind of quickly scroll through it. There we go. And if we want to see this individually, I've also attached to the package our package script. So if we fire it at an angle degree of 20, it shows us our time airborne and it shows us our meters. And of course you can change it up if you like, 75 degrees. And again, it shows us our time airborne and our range in meters. Now for the last question of the assignment, yes, the results did differ from the mathematical analysis of assignment 1. I suspect that the difference occurred because when doing pen and paper math, the rounding of my initial velocity x and y were rounded to the nearest 2 decimal places for ease of math. On the other hand, mathf.sine and mathf.cos are highly optimized, but they use standard floating point precision, which does not accurately represent real non-integer numbers, causing rounding errors in itself. I suspect that neither answer would be entirely correct because both methods do cause rounding errors of their own. One way in which this could be made more precise is to change the float variables to double, which offers 15 to 16 digits of precision instead of 7. And that's everything. Thanks for watching.